Time. I'm very happy today to welcome Professor Vladimir Mitin. Professor Mitin is a SUNY Distinguished Professor, SUNY State University of New York. It's a Department of Electrical Engineering at the University of Buffalo, the State University of New York. Professor Mitin is a fellow of IEEE, so it's Engineering Society, SPIE, which is Optoelectronics Society, American Physical Society, AAAS is a Science Promotion Society, and Institute of Physics, which is a society in UK. He was the chair of the department for 2 terms in the University of Buffalo from 2003 to 2009. It's a period of time from 1993 to 2003. He was a professor in the Department of Electrical and Computer Engineering at Wayne State University in Detroit, Michigan. His fields of specialization are in nanoelectronics, optoelectronics, devices and materials, and currently he is working in the areas of design and characterization of electronic and optoelectronic devices with emphasis on photovoltaic solar cells. And he carries research both in theory, simulation, as well as experimental work. He has more than 230 publications in reference journals, 14 patents, 4 monographs, I read one of those, and 5 textbooks. So please welcome Professor Mitin.
Thank you very much for warm reception. It was really warm after my Buffalo time, so thank you. So now let's try to see if I will be able to combine both. That students will understand what I try to do, and faculty will not say, okay, all is wrong, why we did not get any new results. So what I will try to talk about, that the band structure engineering around for many years, and I think even if you are students and you already were exposed to many maybe examples, and the simples are, if you have semiconductor, then you know that each semiconductor has energy gap, and it's given, determined by God, and you cannot change it. You can change only if you change the material. Yeah? Now, there is a simplest way to do band gap engineering, to change the band gap. If you take material A, material B, and you mix them. You take material A in fraction x, material B in fraction 1 minus x, and in the simplest understanding it will be, you see, band changes from energy gap of material A up to the energy gap of material B, and you are done, yeah? You're already better than predetermined material. The next step, of course, that's more popular, but it's combined also with the first approach. You have material A and material B. They have 2 different band gaps, but you put one on top of another, and what is going on, now you have engineering of your band gaps. You see, you have wider, narrow, but what is advantage also here in this example, immediately you see what is going on, that if you have electron, then electron will go here, because it's smaller energy for electrons there. And if you have holes, then holes will go there, because it's smaller energy. And it's possible to do different combination. Of course, I can move this down so that electron will be in one material, hole is different. So, understandings of electrons and hole, I think that you all may know from electrical engineering, that if now this semiconductor material absorbs one photon, it gives an energy, and it takes electron from the valence band in the conduction band, and you have now electron that can conduct and hole that can conduct also in the valence band. So these are examples of the more or less simple band engineering that is used. And then of course I can move now material, again B or C, and close this. It will be like, for example, thin films. And this thin film between 2 other materials will give me opportunity to have so-called quantum well if this material that I'm interested in very thin. So in the sense now I have 2-dimensional systems. Electron can move only in the plane because this is very thin material. And then of course if I do confinement in this direction as well, you see now it will be very thin wire, and if this will be very small dimensions, it will be so-called quantum wire. Now electrons can move only in one direction. Finally, I can do very small material, like cluster, like it's shown here, and this will be so-called quantum dots, And why it is quantum dots? Because it's became like artificial atom, and now the motion of electron is confined in 3 directions. Advantage of this band structure engineering that now you can change material of the matrix where you put the dot, you can change material of the dot, and you can change the size of that dot. So doing all this, you can change the distance between the levels in these dots. So you use it for the devices. And this is widely used. I just remind you that it's very popular in engineering to produce new materials. What I will talk now about something else that we introduce so-called on top of the band structure engineering, the potential profile engineering. So what we do, it's even easier and simpler to understand that on the first slide, you remember it was here exposed for long. You have Niagara Fall, and here you see this is American Fall, where water coming down because the profile of potential is such that water is going on where the potential is lower. Yeah? Here, I went preparing talk 2 days ago. I went on my backyard, and this is a small creek that I have. And here you see very small island. Here it was a huge change in the potential energy for water. Here it is very small, but what is going on? Water go around this small island, that is potential island, and unable to go on the top of this small piece of the land that is on the creek. And this is what we will do, and this is what I will talk about. If we have a quantum dots, and all we use what people used before, we of course choose the material of dots, material of matrix, we change the properties of the material, but in addition, on top of that, we create the potential profile that now electrons will move between the dots. We will create such a potential profile that like water here is moving in the predetermined direction, yeah? Here it's going around the obstacle. And we would like to see that our carriers will go around quantum dots, and you will understand why do we need it. So now, advertisement of our efforts with this potential profile engineering, what we achieve, why it is good. So here, as advertisement of our efforts, I show that we have improvement in solar cell performance, and I will demonstrate it that now the short circuit current, this is if you have solar cells and you just shorten it and measure what will be the current from the solar cell, we have additional 9 milliamps per centimeter square from the quantum dots that we embed in the material, and we have this only if we start to charge dots. If we don't use charging of the dots, we don't have improvement at all. And second, I will talk, and I will start through this example. It's quantum dot infrared photodetectors, where we have increase in responsivity by 25 times. So I will start with that example, as it would be easier to understand, because the quantum dot infrared photodetector is monopolar device. It's only one type of carriers, and this particular case, it's so-called N-type, or electron conduct current in these devices. So what you have here, already familiar to you picture that I have material of the matrix and dots, you see they are here. I have layers of dots, we have grown material, we put dots. If you are interested in, I can discuss later how you create these dots in the material. But we have layers of dots, and now if we shine light on this material, then electrons that will be in that dot will get energy from the photons and go out of the dot. And as they out of the dot, they can contribute to the current. So if in my material I have the collector at the bottom and emitter on the top, so if I shine light, then I will have current that is proportional to incoming flux of energy from the radiation. And of course, now ideal detector will be the one where all electrons initially are in the dots, nothing in the matrix. So if you measure conductivity of this device, it will be 0 without light, because there are no carriers that can carry current through. But if you take electrons out, then you will have current through the device. Yeah, you have photodetectors. And of course now, changing the size of the dots, material, and so on and so forth, you can choose photodetectors for any practically wavelengths of any energy that you need. Now, what was the wisdom before we start our work? As I need to have electrons that will absorb light, then the wisdom came from the so-called quantum well photodetectors. To have electrons in the dots, I need to dope. And it was clear, if I don't dope this material, it will be all intrinsic, then I will have only band-band absorption, to which I come later. And now people doped, or before our efforts, quantum dots themselves. Because what you need to have electrons in the dots. When you dope, then the electrons go out and they contribute to the current. What is the problem? It's small one, nobody paid attention. If now you take electron out, the dot will be charged positively, yeah? Because you have impurity in, and dot now lost one electron. It would like to have this electron back. And as it would like to have it electron back, you really increase probability for electron to recombine, yeah? So what we suggest that you need to dope this material outside of the dot. As you have impurities here outside of the dot, then electrons go to the lower energy and populate the dot. What is going on? The dot is now charged negatively, the surrounding is charged positively, and you have something like drawn here potential profile. If electron is outside of the dot, then it needs energy to go back. Because as soon as I throw electron out of the dot, it loses energy and moves between the dot, and it will be difficult for the dot, to take electron back. And so depending on the height of the potential band, the time of capturing of the dots in the dot back increases exponentially. So here its probability goes down exponentially, or lifetime really goes exponentially up with the increase of the barrier height. How we control the barrier height? By the doping that is outside of the dot. So now we go fast to the proof. So this is detector. So the popular things to do, we did Monte Carlo simulation. We took into account all what we can do, like all scattering mechanism, and simulate what will be the lifetime of the carriers in material depending on the doping that control the barrier height. As you see, in the small electric field, we have substantial increase of the lifetime, and this is due to the fact that I already mentioned that if electron is out, absorbed photon go out, lose energy, and it's moving here in the bottom of the potential profile, like you have it in the river, like water goes here, it doesn't like to go up. But what happens now if we increase the electric field? At a certain field, like 1 kilovolt per centimeter, you see it's 1,000 volts, we have a substantial drop of the time. We increase lifetime, but when we increase the field, time decrease substantially. What happened? Now, as we say, electron get a lot of energy from the field. So-called electron become hot. They go up in the energy, and now when they move, they can go back now into the dot, because they will go here on the top and can lose the energy. I put it again, I don't know if it is good comparison, but now as electrons, energy, you understand maybe it's better with the water, because now water is here at the bottom, and it will not jump back to American falls because water has not enough energy. But what if I heat this water? Yeah? If water evaporates, if temperature goes up, you know that we have increased evaporation, then mist of water goes up, and now it can go anywhere, and in particular go back. And of course, you know this phenomenon very well. Yeah. So what is the idea? You need first to increase the barrier height, charging dots using outside doping, and second, don't go to the very high voltages, because higher voltages in the detector will really reduce the lifetime. And so here it is shown, like if we have relatively low electric field, then lifetime of carriers increases with the increase of the barrier height. If you have very high field, then practically no dependence. Why it is? Because electrons are always very hot. They are moving in the higher energies and can be really captured into the dots. So to present how good it is for the detectors, you see I show here so-called optical gain. That is a capture time that we can control, as I explained to you, by doping. It's ratio of capture time to the transit time. Transit time is the time that the electron will take to go from one contact to another contact. If I increase the electric field, then if you recall, this capture time first is a constant practically, but as electric field increases, electron go faster and faster through the circuit. So the gain increases. So experimentalists always try to apply as high voltage as possible, because the conventional wisdom that it will continue to go up and up. Yeah? But in reality, what is going on, it reaches maximum because now it will be very fast decrease of the capture time, because the electron will be hot. And to demonstrate that these models are correct, we grew material with different doping, and not only different doping, but different placement of the doping. Yeah? Because what we can do, we can place dopant at the time when we grow quantum dots, and we can place dopant at the time when we grow the barrier between the dots. So here you see that we grow 10 layers of the dots. It's about 50 nanometers between layers of the dots. It's repeated. The same is here, but in these 50 nanometers, in the middle, we put doping. And now I compare the results of the measurements and what is going on here. With increasing the dot charge, we increase the photoresponse of the detector. And it's due to two reasons. The first reason is very simple, because the more electrons, the higher will be absorption from the dots. Because electrons absorb the light and contribute to the current. Second reason is really increase of the barrier. That is why what we have, the same doping with the same approximately number of electrons in the dots, but in the first case, when we dope inside of the layer, when you grow dots, then some impurity goes in the dots, and so the charge of the dots is smaller than the dopant are outside. And again, the same number of the dots, but we have higher doping. Like here, you have increased doping 1, 2, 3, 4, and as you see, we have substantial increase of the photoresponse of the detector due to the fact that we increase the lifetime of the carriers due to repulsive potential. And now I put summary of the first part, where we had one type of the carriers, only electrons, because it was photodetector. And as you see here, creating the repulsive potential of the dots, we exponentially increase the lifetime of the carriers when they are out of the dots, and by that we increase the responsivity of the photodetector, because now the gain become huge, and in some examples we have gains that reach 1000. It means that if you throw one electron out of the dot, it can go through the circuit 1000 times before it will be captured, because it goes in the minimum of the potential profile and does not want to go back in the dot. So now I switch to the second topic. It's about solar cells. So somebody asked me today how solar cells and photodetectors are related. It was maybe not good comparison, but I say they are the same. The only difference that when you do photodetectors, then you try to produce it for a certain frequency or for a certain energy of the photons, and then you detect those photons. Yeah? When you do solar cell, principle is the same. You have light coming, current going through the circuit, but what is now necessary to have? You want to have this detector response to all frequencies. You want to absorb all light that is coming from the sun. But to have to have solar cell now, what regular used, that you have so-called p-n junction. So you will have part of the material that doped by acceptors, part of the material that doped by donors, and so it creates so-called p-n junction, and in the middle, regular, there is, depending on the design, it will be so-called intrinsic region that you don't know. That region might be different in the devices, but I will show you just the principle. So what is the principle now? Now, when light is absorbed, then electron is taken from the valence band in the conduction band, and now as we move this p-n junction or depletion region close to the top, like you see here, light coming from the top. On the top you have p-type material, so light is absorbed, and the thickness of the material regular such that you absorb the light inside of the solar cell. So the light is absorbed here, and as it is absorbed in this depletion region, then you see here the electron that is created has field that will drag electron to the N contact, and the field that we have will drag holes to the P contact. So electron hole pairs separated, and as they separated, they cause current in the external circuit. So you have here contact, so you have this load, and so you have current between P and N regions. Now, at the very beginning, I mentioned to you that each semiconductor material has its own band gap. So what is going on? That the photons that have energy smaller than energy gap multiplied by electron charge will go through without absorption. So what it was for us, for each semiconductor material, I show here a case of gallium arsenide. This is the solar spectrum. This is what we get on the Earth. And this is wavelength of this light that coming from the sun. These are, you see, if we are in vacuum somewhere above the Earth, then of course it will be smooth curve. But these windows are absorption of light by atmosphere. So these frequency of these wavelengths don't come to the surface because they are absorbed by the atmosphere. That is why instead of having here perfect smooth line that you will have in the space, you have these dark. So don't pay attention to this because we can send solar cell also in the space. Then it will be nicer. But what is important that for each material you have the cutoff frequency or cutoff wavelength. Here I show gallium arsenide, so this is 880 nanometers or 1.4 electron volts in the energy. So whatever is with the longer wavelength go through gallium arsenide without absorption. So this is immediately lost no matter what. and this so-called below gap losses, it's 33%. So you cannot have your solar cell more efficient than 100 minus this is 33, because 33 went already through guarantee. Then here it is also shown the thermalization losses. What means thermalization losses? You see that when I show here the band gap, that the photon that has this huge energy that's substantially larger than the gap, it's also produce electron and hole. Yeah? They are there, but what is going on? They will lose their energy scattering and giving it to the photon. So it's also inevitably lost energy. It's also 20% already out. There is no way that you will get those 20% back. And that is why there are some other losses that in principle you can struggle for a little bit to improve. So for each semiconductor you will have a certain maximum possible efficiency that is drawn here, and gallium arsenide, the theoretical efficiency about 30%. So whatever you do, you cannot have more than 30%. This is absolutely like a limit. And for each material, it's its own limit. And as you see, if you go to the wide band gap material, then what is going on? On this land which I'm moving here, I absorb less and less light. Then it's obvious for you that, of course, efficiency goes down because that red amount will be higher and higher. But if you move here, making what narrow and narrow material in this direction, then you again start to lose. Reason very simple. You absorb more light, but the voltage that you can take from the solar cell, it's maximum energy gap divided by electron charge. It's absolute maximum. So you will be unable to make solar cell from gallium arsenide that will give you 1.4 volts. It will be always smaller. It's an absolute maximum. If I go to the zero band gap material, then it absorbs everything. Absolutely everything. But it will be completely zero efficiency of this, because the voltage that I can take from this solar cell will be zero. So, what are the efforts to beat the nature? And the most successful maybe effort is the following: that if we have different material that absorb different frequency or different energy lengths, let's build the tandem or so-called multi-junction solar cell, where the top material will have the widest band gap. And here, for example, shown an example that this is gallium phosphide. So this solar cell absorbs this part of the spectrum, and as you see, it's shown what will be the maximum what can be transferred into the useful. This is lost. Next will be material with a narrow band gap. Before I show you gallium arsenide, you see, so adding on top of gallium arsenide, I win a little bit due to the fact that I reduce the so-called thermalization losses. But now, you see what else here shown. At the bottom, we add germanium that absorb this infrared part of the spectrum. And as a result, I will have the same current going through 3 solar cells, but the voltage will be added, and the efficiency of this cell will be higher, because what I did, I was able to so-called harvest more energy from solar and transfer it into the useful power. So this is a busy slide, and you don't need to go into details. What I want to attract attention to here, it's NREL slide, and they update this all the time. And what is the most important? If you take any point on that slide, you see first going something, efficiency goes up. So here, this is efficiency. So it doesn't matter what system people use, first you have increase in the efficiency. Yeah? Then what happened after this, you come to practically flat path. So here, investment was really productive. You do, for example, here, you see it's recent. Nobody did this before 2000. Nobody did this before 2010. Now, they have very fast increase in the efficiency, yeah? So if you move it here, it was the same 30 years ago, yeah, with different system. But inevitably, what is going on for each system, you come to the absolute saturation, and then sometimes it takes many, many years to put next dot on the plot. You have a little bit, you see, of improvement. Or here, for example, you see how long it took to have that improvement. Because now you need to move to new materials, and the only nice line is here, and these are so-called multi-junction solar cells. You put more junctions, you have higher efficiency, and these are special solar cells, and as you see here, you go to 40+%. So it looks like that these are the best to do, but there are many problems I don't have time now to discuss, and one of the problems is really the cost. The second is really you need to have current matches, because my topic is now different, yeah? So I will not criticize what others did, because it's a great job, but we choose a different way, and this is also belongs not to us. Somebody smart say, okay, why we put these solar cells in series? There is a problem, current matching. What if we put those in parallel? This is my own interpretation of their work. That what it means that now I will put one solar cell like this and the second solar cell inside of the first one. And here it is there inside. What these guys did in 1997 say that now we will have solar cells with efficiency up to 60%, theoretical curve, and I put this one and this one inside, and again I can change here parameters and how they did. They say, okay, we have a certain material, and inside of this material we will put something that will create so-called intermediate band. So to create intermediate band, the easiest, and it was many discussion, to put quantum dots. So you put quantum dots inside, you create so-called intermediate band. Now changing the dot material and so on, I can move these from here to there. What is the advantage now? They say, okay, like before, all photons that have energy larger than band gap of initial material will be absorbed. Now, that band, I am smart enough to make half filled. What means half filled? You have there some electrons, but you have some states. So now, the photon that will take electrons from here and bring there will be absorbed as well. At the same time, the photon that take electrons from here and bring there also will be absorbed. So moving this band around, I can change the portion of these photons, and this will be a perfect solar cell. And theoretically, 60%, and it was many, many, many efforts creating these intermediate band solar cells. Now, I will show you next result. Not the worst, not the best, but one of the examples. And now, what happened? As I have cut off for initial material, people can show, and there are hundreds of papers where they demonstrate, yes, we have additional harvesting, because now we put intermediate bands there, the photons that were going through the device now absorbed, and we have additional harvesting. So this is a spectrum that is absorbed, and this is really contribution to the efficiency. But now what happened, if you look into the performance, then performance went down. You have smaller current and smaller voltages. In some best efforts, the current will be the same or close, and I will show our initial results. The voltage deteriorates. The problem was that in this perfect design, people did not pay attention that, yes, you create additional absorption of the light. But what about the inverse process? Inverse process is really, you create these dots, these carriers absorbing the light. Now the carriers are here, and now the electron can go back on the intermediate band. And the more dots you put, the higher will be these processes work. You increase the absorption, but quantum mechanically you see absorption of this photon and emission of this photon have the same probability, but it might be also thermal absorption of electron from here to there, and the same of holes from there to there. So putting additional dots, creating this very beneficial additional harvesting, you create additional recombination centers. So if you remember the stuff with Niagara Falls, then you create some kind of the holes that are inside of the river. They are invisible and water can go there. So what we suggest that to overcome this problem of reduction of current, and what is most important here, that you immediately understand our idea, that when you increase the absorption there, then efficiency from the higher energetical photons inevitably goes down, because they can recombine now electrons and holes that are produced by these previously important photons. They will be dead before they come to the contacts. So now we come to the same picture that I already introduced to you, and this is the specific case of indium arsenide dots in gallium arsenide. That is the mostly used structure for these solar cells. And what we do, it's again the same story, that we dope. Now, in the previous example, it was obvious for you, yeah? You have photodetectors that are working on electrons, so the doping was obvious. You need to dope this material with such dopant that charge dots negative. But now you have two types of carriers in this material. You have holes and you have electrons. And now what? If you are doping with donors, you create more electrons, but it will be attractive for the holes, yeah? And vice versa. In case of gallium arsenide, what is going on? That the capture of electrons into the dots is 10 times faster than capture of holes. And also, as you see, and it's to some extent to the scale, that here the depth is small for holes. There the depth is large. So when electron is going in, it's practically in. When the hole is going in, it's almost easy go out because it's very small barrier for them. So now we charge the dots negatively, and it will be the same type of the structure as I gave in the photodetector example. Now we will have again growth of gallium arsenide with indium arsenide dots, where we again dope in the dots and out of the dots, or not dope at all. You see, so now we see how everything will depend on the doping. But before going in, I would like to attract your attention to a new mechanism that will also increase the performance of solar cells. That was not in the original design, and this new mechanism is the following: that you see, when we will have the, for example, absorption of the light in the dots, that electron somewhere in the higher level, then this electron, as I already have the electrons initially, I put them in the process of growth. This electron that is produced by the absorption of the light can lose its energy going down, but giving that energy to another electron that goes up. And this is one of the things that can increase the contribution to the current. Then also, even that photons that has huge energy produce electrons somewhere there. Now this electron can really give energy to electrons in the dots and throw those out as well. So it means that now we make it easier for electrons that we dope there and electrons that we produce by the light absorbed inside of the dots to contribute to the conductivity. So now the different plot of the same as I showed to you that what is going on there. It's power conversion to electricity for different material. Gallium arsenide is here, and this is the limit that I demonstrate to you. Then this is the power that is lost. Here it's energy. Power is lost due to subband gap photons that go through. Now, if we absorb these photons, we increase, and theoretically, as I show you, that people show that you can take all this and go to 60%. We already demonstrated that additional 5% increase, red arrow, working for more increasing, using the same idea as people already introduced, predicting this huge benefit, but these huge benefits were killed by the additional recombination introduced by the additional dots. So here is the result that I try to present and show that yes, it's good to have. So that solar cell, and I will compare again with the results from other publications that I just showed before. Here, as you see, 6 different samples shown. And first, it's control cell. That is here with 15 milliamps per centimeter current. And so this is like load curve. If we put quantum dots and will not dope at all, then our solar cell will give approximately the same current, a little bit smaller voltage, so practically almost no change. So it's already a good sign, because in previous example I showed to you that some people have deterioration, but there are some other publications that where you have small increase, that people demonstrate this, yeah, due to some place. But now, if we dope this solar cell with a p-type dopant, then performance decreases substantially. What is going on? We charge dots positively, and I show later that recombination through dots increases. Okay? Now, if we start to dope with n-type, so we charge dots negatively, as you see with the amount of doping, we go higher in the current, and here increase in the efficiency, and we went up to 6 electrons per dot, and so we have, for this particular cell, we have practically 50% increase in the efficiency. But it adds, like I say, adding 5%. So now we emphasize that it does not matter what was your initial cell. If it was with a higher current, you always can increase the current due to the contribution from, I will go there back in a minute, due to the contribution from the infrared. So here it is shown only infrared contribution, and infrared we name that everything what is with a wavelength above gallium arsenide. So we put on the top of the material thick gallium arsenide that absorbs everything. It doesn't go to the solar cell. Whatever gallium arsenide passes, it goes to our solar cell. And as you see, we have additional current that depends on the doping. And this additional current is like, we measured up to 9 milliamps per centimeter square. And in reality, we did not have 9 added because you have some recombination still as well. Here it is, of course, shown as Anna did, that we have introducing quantum dots. We introduce, of course, additional harvesting in the spectrum, and this is just measured results, contribution to the output. And here it's the same level of the doping. Exactly, we introduce 3 electrons or 3 holes per dot, and as you see, we have n dope. Then luminescence from quantum dots is about 6 times lower or 8 times lower than if we introduce p dope. So p doping is really, or no doping, it's also bad, but p doping in particular shows that it's deterioration of performance. So as I already give introduction, the physics behind this is that we have absorption of conventional light in like gallium arsenide matrix. We have additional absorption of lights in the dots. Of course, this shows that light is absorbed like this because we can design the solar cells. You remember that now there are 3 batteries, so 3 solar cells inside here. One that absorbs this energy and above, one that absorbs this energy, you see, starting from the smallest to the largest in the dots. And also this, because throwing electrons and holes out. So the major things, what is new and different is that electrons are now moving between the dots and they don't like to go in, and that is why we have reduced recombination. And here it shows that it's like the creek for the electrons, that they go between the dots. Depending on the number of the dots, we show what is going on here. That you see the dots is this is a dot. In this simulation it is flat, but we have different sizes and different type of simulation, but the reason is still the same. There are layers of the dots that you see here, like AB is along the layer, the cross, and you see that we have cross section that is shown here between C and D, that you have increase and in the potential height that repel electrons from the dots, and it depends on the number of electrons that I put in the dot. You see this 1 electron going up to the 9, and we finished with 6 electrons somewhere here. So as you see, it's quite substantial barrier that prevents electron to go into the dots, and by that it really increases the efficiency, as we show here, in contrast to the previous results of other authors that are overwhelming majority, where they create the intermediate band and then put in more dots. Really what is going on, that you have deterioration of performance in spite of the fact that you have additional absorption. So as I have, it looks like 1 more minute to complete, I will show you that we also prove that the quality of the material improves from the point of view of this conventional so-called diode model parameter. So in the textbook, maybe students took it that like if you have the p-n junction that is a diode, and why it is named a diode, it maybe you remember that this really rectifies the current. Yeah, so if you apply AC voltage to this p-n junction, then current will go in one direction only, and this is what really used in the solar cells. And this is the simplified circuit for the p-n junction, and this is simplified equation for the junction. What is here important, that for reverse bias voltage, the current will be so-called saturation current, and this demonstrates the quality of the junction, because reverse current is controlled by recombination inside of the intrinsic region. And so-called non-ideality factor that is introduced here in the place where the current increases exponentially for the forward bias. You see that current increases here is semi-log's plot, that current increases practically exponentially. So using measurements for different temperature, we determine these parameters of the diode. You don't need even to do solar cell measurements to see the quality of your material, yeah? How good p-n junction you have. So what is here demonstrated, that first I show the ideality factor n. And it's again the same play, like you have reference cells, that is with the dots. So we have at room temperature 1.6, this ideality factor that recognizes a small number. Now, when we put dots and put undoped, you see that this factor increased by a factor of 2. And what is going on? Now recombination goes through the dots. So your PN junction become not as good. The rectifying characteristic of the PN junction is worse. When we start to dope, then you see that we have increasing here with first substantial drop when you have 2 electrons, 3 electrons. With 6 electrons, we have already a little bit worse, but better than in undoped. So we still need to work on this to understand a little bit more and improve. And the same with the reverse current. You see, the reverse current, when we increase, first the current increased practically by 2 orders of magnitude when you put dots but don't dope those. If you start to dope, it drops down. So it means that there is a characteristic of the PN junction really demonstrate that yes, when you charge the dots in, then recombination in the material goes down. This recombination is due to the dots. So here there is a summary. So what I try to demonstrate here that our material with the potential profile engineer help us to reduce recombination using the benefits of the additional harvesting. And so in principle, theoretical value was not predicted by us, can go to 60%. We at least claim that we can compete with multi-junction, that we hope to go to 40%, to be conservative, but this is a possibility to do material really adjustment. So this is a summary for solar cells, and I would like to thank you. And if you have questions.
So we have time for a few questions, please. Questions from the audience.
So one of the things that I missed when you have the intermediate band, is there anything that forbids transitions between the intermediate band and higher level?
Of course no. Of
So
course.
wouldn't that be the same kind of thermal loss of
Yeah, but that's the thermal loss. Yeah, of course, yeah. But people who did this calculation, then they of course took this into account because mostly the maximum efficiency is calculated taking into account only thermodynamics. Only thermodynamics. Nothing else. You see, there is no probability that's on
So the chocolate wins the limit, right?
Yeah, it's chocolate. Yeah. And also, I don't know, I did not discuss here, it was huge activity. It works a little bit in our cells that, like, I heard today name of Victor from Los Alamos. They know how to produce many electron hole pairs with one huge energy photon. Yes.
multi-exciton production?
Yeah. So that also he repeated the paper of Quasar some time ago, and he demonstrates what will be also the absolute theoretical limit. It's a little bit in improving of the Quasar limit due to his effect.
Some other questions? So I have a question. So let's say the quantum dot that you use to probe the molecular reproduction quantum
Yes.
dots, right? And so the main approach that you do charging of the dots.
Yeah.
Would this approach work with some other quantum dots? Let's say obtained by some other means?
Yeah, first of all, it's a good question, thank you. And what we try to find today, the person who will work with us on silicon germanium, because silicon is widely used in solar cells. And germanium dots in silicon that were also produced by other people. We need only to use our technology to charge those. The advantage of germanium and silicon is that if I go fast to the slide that I showed you before about the band structure,
Small discontinuity.
for holes, no, that will be the following. Electrons in germanium has this bulk. So electrons would be never captured in the dots. For holes, there is a potential depth. So if we charge now dots positively, then this will be like perfect material for solar cells, because now electron-hole recombinations through dots should be completely like, no, not completely, but eliminated, because electrons does not go into the dots at all, because initially there is a barrier. And for holes, you have the dip there. So holes going in, and of course you will have more complicated, like indirect recombination. There are some things, but this is very interesting material. So depending on the material pair, you need to consider what type of the doping you introduce.
Of course.
If you charge your dot too much, you will run into very
That will,
combination.
exactly. No, but we need to understand the role of the doping, and we will do it, but for everything it's necessary to have like time. So we don't know what will be. You see that?
Okay.
Yeah. So I cannot answer this question as of now. Just to show that we have some candies in front of us, or some carrots, we already have better results that I showed just now. And something will be presented at SPAE in Baltimore at the end of this month, and some we will send in the journal very soon. But as it mostly what we do patent publication, so we think that this is something that we need to like do slowly in the sense of releasing of the results. So we have now higher efficiency already than demonstrated today, and it's measured, demonstrated. So there is some other tricks that I did not mention today because they in the process of the like publication, and yeah. But there is a material possibility. We focus on the material.
Okay. Any other questions from the audience? So if there are no questions, let's thank you very much.